Hello humans, my name is Professor Leach, and today we are going to talk about some trigonometric identities. Let's recap what we need to know. We spent a lot of time building up a knowledge base where we need to know our exact values. That is the sine, cosine, and tangent of 30, 45, and 60-degree reference angles in quadrant 1, quadrant 2, quadrant 3, and quadrant 4. We need to know that these three reference angles, when paired with sine, cosine, and tangent, will give us numbers like root 3 over 3, 1/2, root 2 over 2, root 3 over 2, 1, and root 3. We just need to pair all these up with some pluses and minuses based on our quadrants. And then the last thing that we need to add is what's going on with sine, cosine, and tangent at the boundaries of the quadrants. So 0 degrees, 90 degrees, 180, 270, and 360, which is back to 0 again. The reason that we want to be able to do this is that we want to be able to calculate sine, cosine, and tangent for any angle, not just an acute angle, not just an angle between 0 and 360, but any angle. So that's the idea. We want to be able to calculate sine, cosine, and tangent. We want trig functions. We want trig functions. Let's say trig function values of any angle. Not just acute angles, not just between 0 and 360, any angle. We want ones past 360 and before 0. That's the negative ones. Any angle. After this, we need to turn our angles into real numbers because we also want to apply trigonometric functions to the real numbers instead of that can represent anything. That can represent things, quantities. I knew that there was a word there somewhere. We want to apply trig functions to real numbers, that is, quantities that are not just measuring angles. That would be the next stage. So in the future, we also want to apply trig functions to quantities other than angles. Trig functions, in particular sine and cosine, are really good at modeling things that go up and down and are periodic, like sound waves, or waves, or pendulums swinging back and forth. Anything that kind of goes up and down and up and down and repeats on a certain period. So we want to be able to apply those kinds of functions to things other than angles. Right now, our trig functions are just being applied to angles. And that's fine. We can get a lot of use out of that. But we want to apply trig functions to more things. All right. So before we do that, we want to introduce, produce, talk about some trigonometric identities. If you would recall, we've been going all the way around the unit circle. So I don't need a big unit circle. I just need, let's see, go. So on the unit circle, we can, if we have a point on the unit circle, the equation of the unit circle is x squared plus y squared is equal to 1. It's a circle with a radius 1 centered at the origin. So the equation for a circle of radius 1 centered at the origin is that x squared plus y squared is equal to 1. If we have a point on this unit circle, and if theta is the angle from the positive x-axis to the terminal side of the angle, then we have coordinates here on the unit circle x, y. And what we found is that on the unit circle, the x-coordinate is going to give us the cosine of that angle, and the y-coordinate is going to give us the sine of the angle. So the coordinates of the point on the unit circle are cosine and sine. The x-coordinate is the cosine of theta. The y-coordinate is the sine of theta. That helps us remember what's positive where. Cosine is positive where x is positive. So cosine was positive in quadrants 1 and 4. Sine is positive where y is positive. Sine is positive in quadrants 1 and 2. Tangents is positive when cosine and sine have the same sign, and that would be in quadrant 1 where they're both positive, cosine and sine are both positive, and in quadrant 3 where cosine and sine are both negative. So with this in mind, we get lots of cool identities just coming from the unit circle. First, we notice that x squared plus y squared is equal to 1. That's the equation that describes this circle. And from that, if I replace x with cosine theta, so we notice that x equals cosine theta. So since x is cosine theta and y is sine of theta, I can replace those in the equation for the circle and come up with an identity involving cosine and sine. So x squared plus y squared is equal to 1. I can replace the x with cosine theta. And y with sine of theta. And get that the square of cosine theta plus the square of sine of theta is equal to 1. An important relationship between cosine and sine. So start with the equation for the unit circle. Replace x with cosine theta and y with sine theta, and we get this important relationship between cosine and sine. And we get this really important relationship with cosine and sine. Since I spent Monday talking about how parentheses work and how we need to be able to read what's going on in an expression, notice that I'm being not that excessive. I'm trying to be careful about where I put my parentheses. To read this expression, cosine theta and then squaring on the outside, the cosine goes first, and then we square the result. Here, the sine goes first. We take the sine of the angle first and square the result. So cosine of 45 degrees squared would be the cosine of 45, which is root 2 over 2. Then we would square that and get 2 over 4, or 1/2. Here's the thing that we need to get used to. Mathematicians back in the day we got really tired of writing these parentheses all the time. And so we're like, well, hey guys, let's come up with some shorthand for the square of the cosine of an angle. And then we were all ready for that. So we're going to write this way. We're going to write this, oops, I still want the cosine highlighted in the pink. Cosine of theta. And then instead of putting this whole thing in parentheses and putting the square on the outside, we're going to write this as cosine squared theta. And we're going to read it as cosine squared theta. This is shorthand notation for the square of the cosine of theta. So in that sense, it's a good notation, because that's what this is, the square of the cosine of theta. Because we do the cosine first, then we square it. So we'll often write this as cosine squared plus sine squared is equal to 1. But it's important that we all recognize that when I write cosine squared theta, I mean the square of the cosine of theta. That's why it makes sense to put the square up in here. Too often when we're taught to read math, we're taught to just spell math. So we say things like cosine of theta squared, but that is not what this expression says. Speaking cosine of theta squared, it means square the theta, then cosine, but that's not what we want to do. We want to cosine the theta, then square the result. So it makes sense to write it as the square of the cosine of theta. But because we're using English, and English is terrible at communicating math, we're going to just read this as cosine squared theta. Because we just spell things instead of speaking properly. Math is better for communicating math. So the question is, what language is better for communicating math? I just know that English is bad at it. It's this weird written language. We have to get used to the writing, but the speaking of it, we're terrible at. So I don't know, maybe there is a language that's out there that's better. I need to learn more languages and watch people teach math in more languages so I can see if they just spell things as badly as commonly as we do. Because I think that is the source of a lot of struggle in math, is that we speak it a certain way. And we think we could speak it in all kinds of different ways. And that really just kind of confuses things. So we've got this important relationship with cosine and sine. If we see we could see some examples of this. This is called the Pythagorean identity. Well, I shouldn't say the Pythagorean identity. I should say it's one of the Pythagorean identities. The most important one that you need to remember is that cosine squared plus sine squared is equal to 1. And when I say it that way, I'm also being lazy. I mean cosine squared theta plus sine squared theta is equal to 1. And I'm also being lazy when I say it that way because I'm just spelling it. The sum of the squares of cosine of an angle and the sine of an angle is equal to 1. But who wants to say that all the time? It's the same reason that you say the Pythagorean theorem is a squared plus b squared equals c squared, even though that relies on a lot of stuff that we aren't saying. The sum of the squares of the legs of a right triangle is equal to the square of the hypotenuse. That's why we want to say a squared plus b squared equals c squared, because it's nice and easy to remember. So if we just plug in a value, leave a couple of lines in here, but if we just plug in a value, if we want to calculate, say, cosine squared of 30 degrees plus sine squared of 30 degrees, we have to remember what these expressions mean. Cosine squared 30 means the cosine of 30, or the square of the cosine of 30. See how hard it is to speak this properly? Sine squared 30 means the square of the sine of 30. We know that the cosine of 30, because we spent time knowing our values, we know that cosine of 30 is root 3 over 2. And we know that the sine of 30 is 1/2. It might be that I was able to get cosine of 30 as root 3 over 2 because I know sine of 30 is 1/2. And I know it goes root 1 over 2, root 2 over 2, root 3 over 2. And so the 30 of the sine is the 60, or the 60 of the sine is the 30 of the cosine of 30. But we still need to square these. Root 3 over 2 squared. Root 3 squared is just 3. 2 squared is 4. 1 squared is 1. 2 squared is 4. 3/4 plus 1/4 is 1. This does not prove that the cosine squared theta plus sine squared theta equals 1. This just is a piece of evidence saying, here's an example. Because this is an important relationship between cosines and sines. Any questions? So here's one Pythagorean identity we should recognize, but we should be able to see it in two different forms. This says we can replace cosine squared plus sine squared with 1. But I can also subtract a sine squared from both sides and find out that cosine squared is 1 minus sine squared. So we should also recognize this as cosine squared is 1 minus sine squared. And since we can do that, there's no reason we shouldn't also just solve for sine squared. So cosine squared theta plus sine squared theta is equal to 1. 1 minus sine squared theta is equal to cosine squared theta. 1 minus cosine squared theta is equal to sine squared theta. So we're getting a couple of Pythagorean identities here. Not a couple, 3. All communicating the same information. In the same way that 2 plus 3 equals 5 communicates the same information as 5 minus 3 is 2, or 5 minus 2 is 3. 3 ways of saying the same, containing the same piece of information. The one that we use is the one that's most useful to us at the time. Also on the list of Pythagorean identities, more variations. If we start with cosine squared theta plus sine squared theta is equal to 1. If we take this equation and divide everything by cosine, by cosine squared. If we divide every term in this equation by cosine squared theta, we get a new form of Pythagorean identity. Cosine divided by cosine is equal to 1. Sine divided by cosine is equal to tangent. And 1 divided by cosine is the secant. So we get this new Pythagorean identity based on cosine squared plus sine squared is equal to 1. So here's another important relationship. 1 plus tangent squared is equal to secant squared. So let's put that on the list of Pythagorean identities. But this is a piece of information that says essentially 2 plus 3 equals 5, so I need the other two versions of it. 5 minus 3 is 2, and 5 minus 2 is 3. So I can solve this for tangent by subtracting 1 from both sides and come up with the identity tangent squared theta is secant squared theta minus 1. And I can also solve for, so this is solve for secant, solve for tangent. I can also solve for the 1 and say that 1 is secant squared minus tangent squared. So now is when things start to get a little bit questionable, because you're like, oh man, this seems kind of excessive. Do we have to memorize all this? And I'm like, oh no, you don't have to memorize all this. You do have to remember all of this. But it all comes from a very reasonable spot. Remember the unit circle, x squared plus y squared is equal to 1. Remember that on the unit circle, the x is the cosine theta and the y is the sine of theta. And so that tells you that cosine squared plus sine squared is equal to 1. The rest of it is just either subtracting or dividing by cosine to transform cosines and sines into secants and tangents. Any questions? So in this case, I use this important relationship here, the relationship between sine and cosine and tangent. So these are quotient identities. Because it expresses one trig function as a quotient of some other trig functions, specifically that tangent of theta is sine theta over cosine theta. This makes sense in a lot of different contexts. Remember that sine theta is, in the case of opposite, adjacent, and hypotenuse, sine theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. And if we divide these two, I'm going to write it as division. So opposite over hypotenuse divided by adjacent over hypotenuse. That means opposite over hypotenuse times adjacent over hypotenuse, because division is just multiplication by reciprocals. Not because fractions, because numbers. So this is opposite over hypotenuse times hypotenuse over adjacent. And that tells us that tangent is opposite over adjacent, which we already knew, but now we can see how opposite adjacent is just the quotient of sine and cosine. Also, since cosine is at the x on the unit circle, since cosine is x and sine is the y, we can look at this from a unit circle standpoint. And we can say that the tangent of theta is sine theta over cosine theta. And we can apply the unit circle, where the sine is y and the cosine is x. The reason that we would want to do this is that this will show, since tangent of theta is just y over x on the unit circle, this will explain why tangent is positive in the first and third quadrants. Because tangent is positive when x and y have the same sign, positive and negative. In the first quadrant, x and y are both positive, and in the third quadrant, x and y are both negative, so dividing them, the negatives cancel and we get positive. Any questions? It's all connected. This is the point where I need that picture from It's Always Sunny in Philadelphia with the board and all the strings connecting it. Or any movie where you want to depict some crazy person making connections in a conspiracy by like putting a bunch of stuff on the walls and then connecting it with like yarn. There's a word for those boards. I can't remember what it's called. Or can I? I actually can't. So we want to see that all these things are connected. We want to see them connected in all of our definitions, our right triangle definitions and our unit circle definitions. So we're just trying to put all these things together. It takes a long time because we want to put it in one piece at a time, but we always want to make sure that we connect it to everything that's come before. Any questions? Because there's one more type of identity that we need to identify. So notice that there in quotient identity, there should be two. Oops. String theory is different. String theory is about how matter is made up in the universe. Pythagorean identities, there should be 9. So I'm deliberately leaving some stuff out. Or am I? I'm going to add or am I to everything I say now. Or will I? See, it's already started. So the other identities that we have are called reciprocal identities. And I've used one of these already. The one that I specifically used is that secant of theta is 1 over cosine theta. Secant of theta is 1 over cosine theta. There are 3 reciprocal identities. Secant is 1 over cosine, cosecant, cosecant theta is 1 over sine theta. And cotangent theta is 1 over tangent theta. So these are identities that we should be familiar with. These are just how we define the trig functions secant, cosecant, and cotangent. We came up with these trig functions because we found that we were using the reciprocal of the cosine and the reciprocal of the sine an awful lot. And so we're like, well, I'm tired of writing 1 over cosine all the time and 1 over sine all the time. Let's come up with a name for those reciprocal functions. This was back in the day where we didn't have things like, PS4s and television. So we was like, well, let's just hang around coming up with names for things. So writing this 1 over cosine is getting a little cumbersome. So let's give it a name. So we called it secant. Like I was there. So there are 3 reciprocal identities that we should know. Should be 3. Oh, wait, there they are. But there should be 2 quotient identities. Tangent is sine over cosine, and then there's another one. I bet you can guess what it is. And then there's another set of 3 Pythagorean identities, because I said there should be 9. One for each of the rings given to the race of men. That's a Lord of the Ring reference. I don't know if y'all saw that movie. Any questions, comments, or snide remarks? There's going to be more quizzes on knowing your values. Just like before, you can redo the quizzes. So if you don't get all the problems, do the problems over again until you do, because that's how we learn things. We don't learn things because someone took off points and told us that was wrong. We learn things by taking the wrong things and fixing them and doing them right. But it requires responsibility on our part to actually make an effort to learn things and not just, I will keep doing this until I get the points. Yay, points. Because that's, I mean, I don't even know why you would want to do that. Actually, I know exactly why, because you just want the points. Because you're not here for an education, you're here for a degree. And if you had enough money, you would just buy one. You'd just be like, well, hey, Harvard, please give me a degree. And Harvard's like, oh, well, do you want to take some classes? And you're like, oh, no. I want to skip that part. Very well, here's your degree. You're like, oh, is this in math? No. You're actually going to have to do work for the math one. Oh, I'll pick some other one. Well, I have to go to class. No. We have people that will do that for you. I don't know why all of a sudden Harvard is using that accent, but there it is. Don't be offended if you're planning on going to Harvard, or if you know people who are at Harvard, because I'll also make fun of Yale, or Stanford, or Berkeley, or Cal State Hayward, or, you know, anywhere. It's all ridiculous. Skyline, CSM. Apart from that, I believe that that's it. I'm done. Email this to your grandma, and I'll see you some other time.